Hi everyone, imagine you're packing for a weekend road trip. You want the fastest route, but you don't have time to check every single back road. That's exactly what approximation algorithms help us do in computer science. They find good enough solutions quickly when perfect answers take too long. In this course with Yaoting Huang, we'll explore the key ideas behind these algorithms, learn how to measure how close they get to the ideal, and see real-world applications from network design to scheduling. By the end, you'll be able to craft your own approximation strategies and analyze their performance. Let's dive in. Now, let's dive into nitrogen monophosphide complete problems. First, what does nitrogen monophosphide hardness mean? It means every problem in NP can be reduced to a problem Q in polynomial time. If Q has that property, we call it nitrogen monophosphide hard. Next, NP-complete problems are exactly those nitrogen monophosphide hard problems that also lie within NP. Despite decades of research, no one has found a polynomial time algorithm for any nitrogen monophosphide hard problem, so we currently believe P does not equal NP. In the Venn diagram here, NP is shown as the large set, P is a smaller subset inside it, and nitrogen monophosphide complete is another subset of NP that sits outside P, illustrating that nitrogen monophosphide complete problems are in NP, but unlike those in P, have no known fast solution. Building on that, today we ask, how hard is nitrogen monophosphide hard? So far, our best algorithms still run in exponential time, on the order of c to the power of n for some constant c, as the input size n grows. In other words, there's no general way to guarantee an optimal solution in polynomial time for every instance. This ongoing challenge is captured perfectly by the image of a frustrated child covering her eyes, reminding us just how tough these problems can feel in practice. So how can we tackle these computationally tough problems? Let's explore 4 broad strategies. First off, exact algorithms guarantee an optimal solution, but they can be costly. Common techniques here include branch and bound methods and fixed parameter approaches. Next, heuristic and meta-heuristic searches sacrifice guaranteed optimality for speed. These methods focus on promising regions of the solution space. Think taboo search, genetic algorithms, or ant colony optimization. Third, statistical learning approaches build models from data, capturing underlying patterns. Examples include expectation maximization and Gibbs sampling, which let us infer structure and make informed guesses. Finally, approximation algorithms, highlighted here in red, deliberately settle for near-optimal answers in polynomial time, striking a balance between quality and efficiency. Each of these strategies represents a trade-off between solution quality and computational cost. Choosing the right one depends on your problem size, available resources, and required precision. Now let's take a closer look at approximation algorithms. They tackle hard optimization problems by trading perfect accuracy for efficiency. Rather than seeking the exact optimum, they deliver solutions provably close to the best possible, all within polynomial time. Key approaches include deterministic versus randomized methods. The former follow a fixed procedure, while the latter use randomness to boost expected performance or simplify the process. Relaxation techniques. Problems are converted into simpler, often continuous forms, like linear or semi-definite programs, and then rounded back to valid solutions. Polynomial time approximation schemes, PTAS. These algorithms let you dial in how close you want to get to the true optimum, with running times that grow as you demand tighter guarantees. Moving on, our primary reference is the book Approximation Algorithms, published by Springer Verlag in 2001. It's written by Vijay V. Vazirani, a professor in Georgia Tech's College of Computing. This text offers a comprehensive treatment of approximation techniques, including greedy strategies, primal dual methods, randomized rounding, and more, and will serve as the foundation for our study of efficient algorithms for nitrogen monophosphide hard problems. Building on that foundational work, we turn to the 1996 volume Approximation Algorithms for Nitrogen Monophosphide Hard Problems, edited by Dorit S. Hochbaum of the University of California, Berkeley. On the left, you see Professor Hochbaum. Her deep expertise in industrial engineering and operations research shaped every chapter of this collection. On the right is the book's cover, which unites key techniques and theoretical insights for crafting approximation methods across a wide spectrum of NP-hard optimization problems. This text will serve as the cornerstone for our exploration of approximation strategies. Building on Hochbaum's insights, let's unpack what makes an approximation algorithm tick. At its core, such an algorithm returns an approximate solution while satisfying three essential criteria. First, feasibility. It must always produce a valid or feasible solution. Second, tractability. It has to run in polynomial time so it scales efficiently even as problem size grows. Third, quality. Its output must be provably close to the optimal solution. By meeting these requirements, we gain a powerful trade-off, sacrificing a bit of exactness to achieve reliable, efficient solutions for problems that would otherwise be intractable. Building on that idea, let's look at a simple four-city case in the traveling salesman problem. The optimal tour ABCDA has a total cost of 20 plus 30 plus 12 plus 35 equals 97. Now imagine our approximation algorithm returns ACDBA instead for a cost of 42 plus 12 plus 34 plus 20 equals 108. To quantify its quality, we divide 108 by 97, giving about 1.1134. If the algorithm picked a different order, say ACBDA, the cost jumps to 141, yielding a quality of 141/97. These examples show exactly how we gauge an approximate solution's performance by comparing its cost to the optimal. Building on our previous comparison of approximate tours, the quality of an approximation algorithm is captured by its approximation bound. For any input of size n, let C be the cost produced by our algorithm, and let C times denote the cost of an optimal solution. We then consider the worst-case ratio between these two values, either C divided by C times or C times divided by C, whichever is larger. That maximum ratio is called RHON. An algorithm whose output always satisfies max.x C divided by C times divided by C is less than or equal to RHON. Is known as a WRHON approximation algorithm. Building on that, an approximation algorithm guarantees a solution that stays close to the true optimum. To see exactly how close, we compare its cost C with the optimal cost C times. We then define the approximation ratio, RHON, as the larger of the two fractions. C toms and C toms C, formally, RHON, equals max C. The closer RHON is to 1, the better our algorithm approximates the optimal solution. So building on our discussion of approximation ratios, today we introduce the notion of an approximation bound. An algorithm that delivers solutions close to the best possible is called an approximation algorithm. To quantify just how close it gets, we compare its cost C to the optimal cost C times. Specifically, we define the performance ratio RHON for input size n as the maximum of C divided by C dimes and C divided by C, so RHON equals max C dimes C times C dimes. This single number captures our worst-case deviation from optimality. To establish useful guarantees, we then derive tight upper and lower bounds on both C and C-DOF and analyze how these bounds relate. By doing so, we can confidently state how well our approximation algorithm performs across all possible inputs. Now that we've introduced approximation bounds, let's see them in action on a classic problem, the vertex cover. In any undirected graph, our goal is to pick the smallest possible set of vertices that touch every edge. In other words, for each edge, at least one of its two endpoints must belong to our chosen set. In the diagram, the orange nodes form a valid cover. Every line is incident to an orange node. Because no edge is left uncovered, this set is indeed a minimum vertex cover for the graph shown. Now that we've defined the vertex cover problem, let's see a simple approximation algorithm in action. We start with an empty cover set C and let E' be the full set of edges in our input graph. As long as E isn't empty, we pick any edge, U, V, add both U and V to C, and then remove from E every edge that touches either U or V. We repeat this process until no edges remain, and finally return C. This greedy strategy guarantees every edge is covered, and it produces a vertex cover whose size is at most twice that of an optimal solution. Moving on from vertex cover, let's now watch how a matching evolves step by step on a 7-vertex graph. Here, unmatched vertices are shaded one color, matched vertices another, and the edges in our current matching appear thick and blue. 1. We begin with every vertex free and no matching edges. 2. First, we pick edge B-C and mark B and C as matched. 3. Next, we add E-F to the matching, shading E and F accordingly. General Jenner. 4. Then we include D-G, giving us a provisional matching of 3 edges. 5. At this point, the algorithm searches for an augmenting path, a path that alternates between unmatched and matched edges and starts and ends at free vertices. 6. Once it finds that augmenting path, we flip the roles of matched and unmatched edges along it, increasing the matching size by 1. 7. The final diagram displays the maximum matching after this augmentation. Because each edge is only examined a constant number of times during the search and flipping steps, the overall running time stays linear in the number of edges, OE. Building on our matching construction, let's now analyze how the size of our approximate vertex cover compares to the true optimal cover. At the top of the slide, you'll see, from left to right, our original graph, the same graph with the chosen set A of edges highlighted, and finally the approximate cover formed by taking both endpoints of each selected edge in A. Below this, we introduce C times to denote the size of an optimal vertex cover, and C for the size of our approximate solution. Our goal is to bound the ratio C dividable to Radger. So what's the smallest C tons could possibly be? Well, every edge in A must be covered by the optimal solution, which means C seen times has to include at least one endpoint from each edge in A. Immediately then, we get the key inequality. A is less than or equal to C. This simple yet powerful lower bound on C is the cornerstone for establishing our approximation ratio. Now, building on that lower bound insight, let's walk through the approximation guarantee for our simple greedy vertex cover algorithm. We'll track 3 quantities. C time equals the size of an optimal vertex cover. C equals the size of the cover produced by our algorithm. A equals the set of edges the algorithm selects during its run. Here's what happens each time the algorithm picks an edge from A. It adds both endpoints to C and then removes every edge incident to those vertices. As a result, no 2 edges in A can share an endpoint. Each chosen edge contributes exactly 2 vertices to our cover. From this, we get C equals 2. On the other hand, any valid cover, even the optimal one, must cover every edge in A, so it needs at least one endpoint from each of those edges. That gives us is less than or equal to C. Putting these inequalities together yields C equals 2 is less than or equal to 2 C's names 20, which shows our algorithm is a 2 approximation. Building on our 2 approximation guarantee, let's walk through how the algorithm actually works. We start with an empty set C and a working copy of the edge set E's. As long as E still contains edges, we pick any edge U, V, add both U and V to C, and then remove every edge incident on U or V from E. We repeat this until no edges remain, and then return C as our vertex cover. The key insight is that each time we add a pair of vertices, we eliminate at least one edge, and by charging every selected edge to the optimal cover, we can be sure our final C is never more than twice as large as the minimum possible. Building on that example, let's take a closer look at approximation algorithms and how we gauge their quality. The standout result here is the 2 approximation algorithm, which guarantees that, even in the worst case, its solution cost is no more than twice that of an optimal solution. Remember, this is strictly a worst-case bound. It doesn't imply the algorithm always beats other methods on every input. To fairly compare different approximation algorithms, we examine their worst-case ratio. The smaller this ratio bound, the closer an algorithm's guaranteed performance is to the true optimum, and the better the algorithm. Building on our discussion of approximation ratios, let's revisit the classic traveling salesman problem. Imagine a complete weighted graph of 4 cities, A, B, C, and D, where each connection carries a specific travel cost. Our goal? Find a route that visits every city exactly once, returns to the starting point, and yields the lowest possible total cost. In this example, the pairwise costs are AB 20, AC 42, AD 35, BC 30, BD 34, CD 12. Even with just 4 cities, the number of possible tours grows deceptively fast, showing exactly why pinpointing the optimal path can be so challenging. This slide walks through the basic steps of genome assembly. At the top, you see the original genome drawn as one long, continuous sequence. Sequencing machines then chop that strand into many shorter fragments, or reads. In the middle panel, we've picked out 2 example reads that overlap. One ends in C, 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 T, T, A, A, and the next begins with that exact string. On the right, a second read overlaps through C, A, C, T, T, and carries on into A, T, G. By detecting these overlaps, we merge the first and second reads into a longer contig. Finally, in the bottom panel, those merged segments recreate a continuous stretch of the genome. In practice, this overlap and merge process repeats across millions of reads to reconstruct the entire original sequence. On this slide, we introduce a special case of the traveling salesman problem, in which every edge cost satisfies the triangle inequality. In plain terms, the direct route between any 2 cities is never more expensive than taking a detour through a third city. Because of this property, we can design efficient approximation algorithms, something that's far more challenging for the general TSP. Mathematically, we write C av u, W is less than or equal to C av u, V plus C av v, W for all choices of u, v, and w. To see this in our example graph, look at cities A, B, and C. The direct cost from A to C is 42, while the alternate path via B costs 20 plus 30, or 50. Since 42 is less than 50, the triangle inequality holds here. Every other triple in the graph likewise satisfies the inequality, illustrating why this special case lets us approximate the optimal tour much more effectively. Building on the triangle inequality case we just discussed, this slide introduces the metric traveling salesman problem, where every edge cost satisfies. Cu, W is less than or equal to Cu, W plus C of v, W. In plain terms, going directly from U to W never costs more than detouring through versus our goal? To find the shortest possible tour in such a metric graph, below the inequality, you'll see a sample network of 6 nodes with edge weights shown. The bolded path is one candidate tour. It links the lower left node to the center for 10, climbs up to the top center for 2, moves across to the top right for 6, descends to the lower right for 10, and then returns along the bottom for 2. Thanks to the triangle inequality, any shortcut you insert can only shorten, never lengthen, the tour. That key property underlies both exact and approximation algorithms for metric TSP. Building on our discussion of metric graphs, let's turn to the minimum spanning tree, or MST, of a weighted graph G. An MST is a spanning tree that connects every vertex without forming any cycles, and it does so with the smallest possible total edge weight. On the right, you see an example graph with 7 vertices. The orange edges mark its MST. Here's how they link up. A 3-weight edge from vertex F to the lower left node. An 8-weight edge from F to the lower right node. A 2-weight vertical edge up to the center. A 9-weight edge across to the right. A 4-weight edge climbing to the top. A 5-weight edge back to the upper left. All heavier edges, like those of weight 6, 10, or 14, are omitted, since including any of them would only increase the total cost. Now that we've seen an MST in action, let's talk about why the minimum spanning tree problem is a staple in every algorithm textbook. It's one of the clearest demonstrations of how a simple greedy strategy, adding the next lightest edge at each step, actually guarantees an optimal spanning tree. Beyond its theoretical appeal, MST algorithms serve as essential building blocks for a wide range of graph problems, offering fast, approximate solutions in areas like network design and clustering. By mastering MSTs, you not only gain a powerful practical tool, but also a deeper appreciation for the elegance and strength of greedy techniques. Building on that greedy perspective, Kruskal's algorithm begins by initializing an empty set T and treating each vertex as its own component. It then sorts all edges by increasing weight. Going through the sorted list, it examines each edge. If the two endpoints lie in different components, the algorithm adds that edge to T and merges the components with a union operation. This process repeats until T spans every vertex. On the right, you'll see an example graph where each number indicates an edge's weight. The edges highlighted in orange are selected by Kruskal's rule in ascending order, while the gray edges are either heavier or would form a cycle. The final result is a minimum spanning tree connecting all vertices at the lowest total cost. Now let's turn our attention to Prim's algorithm, which grows a minimum spanning tree one vertex at a time by maintaining three things. 1. A set Q of all vertices. 2. A key array that, for each vertex, records the weight of the cheapest edge linking it to the tree so far. 3. A parent pointer P that tells us which vertex gives that best connection. We start by assigning every key an infinite value, except for our chosen root R, whose key is set to 0. Then, in each iteration, we extract min from Q to pick the next vertex U with the smallest key. For every neighbor V still in Q, if the edge, U, V, is lighter than the current key, we update P fades fran 2 and key equals U and key equals WW, V, Windexton. On the right is our sample weighted graph. Let's say we choose node 5 as the root. When we remove 5 from Q, we examine its neighbors 4, 0, 2, and 3. We update their keys to the weights of edges. 5 to 4 equals 6, 5 to 0 equals 14, 5 to 2 equals 5, and 5 to 3 equals 10, and set each parent to 5. In the diagram, the edges 5 to 4, 5 to 0, 5 to 2, and 5 to 3 light up in orange to show these new best connections. Next, Prim's algorithm picks the vertex with the smallest key, in this case, node 2, via weight 5, and continues adding the cheapest adjacent edge in exactly the same way. The tree grows one vertex at a time until every vertex has been included. Building on our minimum spanning tree discussion, here's a simple 4-step strategy for approximating a traveling salesman tour when distances satisfy the triangle inequality. 1. Pick any vertex to serve as the root, ORIC. 2. Build a minimum spanning tree of the graph using your favorite MST algorithm, ORIC. 3. Perform a pre-order walk of that tree, recording the sequence of vertices you visit. 4. Use that sequence as your tour. Just visit the vertices in the order you recorded. This neat approach guarantees a tour whose total length is at most twice the optimum. Building on our MST example, here's what's happening on this slide. On the left, we start with 8 isolated vertices labeled A through H. In the center, we've added edges to form a spanning tree. T, A connects to B and D, B branches out to C and H, D extends to E, and E splits into F and G. Finally, on the right, we turn that tree into a tree decomposition by grouping vertices into overlapping bags. One bag contains A, B, D, another contains D, E, F, G, and a third contains B, C, H. Notice how every original edge lies entirely within at least one bag, and each vertex appears in a connected region of the decomposition tree. This simple tree, with its overlapping bags, perfectly illustrates a valid tree decomposition. Now, building on our previous example, let's start with 8 isolated points labeled A through H. First, we form a tree T. We connect A to B and D. B branches off to C and H, and D links to E, which splits into F and G. Next, in the third view, we highlight 2 subtrees of T, one containing A, B, C, H, the other containing D, E, F, G. Finally, we overlay T with an auxiliary graph H by adding 3 extra edges, between A and D, between C and H, and between F and G, showing how T and H come together in this example. Building on that, Let's walk through a concrete example with 8 points labeled A through H. In the first panel, we start with the raw point set scattered across the plane. Next, we compute a minimum spanning tree T that links all the points with the smallest possible total length. In the third panel, we duplicate each edge of T to create an Eulerian tour, shown here by the gray loop that visits every vertex. Then we add a minimum weight perfect matching on the odd degree vertices, combining tree edges and matching edges into one connected multigraph H. Finally, the bottom right image shows H types, the true optimal Hamiltonian cycle, for comparison. You can see how our construction yields a valid tour whose length stays within the guaranteed approximation bound. Building on our previous example, let's turn to the approximation ratio H divided by H times. Here, H is the cost of our approximate tour, H tie is the cost of the true optimal tour, and T denotes the cost of a minimum spanning tree. To get a lower bound on H TOS, notice that removing any single edge from the optimal tour produces a spanning tree. Call its cost T. Since the optimal tour must cover at least T times, and T times can't be smaller than the minimum spanning tree cost T, we conclude H times is greater than or equal to T. With that lower bound in place, our next step is to establish an upper bound on H so we can pin down the full ratio H divided by H times. To establish our upper bound on H, we start with a minimum spanning tree on 7 vertices. Then we double every edge to form an Eulerian graph. Traversing that doubled tree gives the walk A, B, C, B, H, B, A, D, E, F, E, F, E, G, E, D, A. And because each edge appears twice, the total cost is exactly twice the cost of the original spanning tree. Next, we shortcut all repeated visits to produce a true Hamiltonian cycle, A, B, C, H, D, E, F, G, A. By construction, none of these shortcuts can increase the path length, so the cost of our approximate TSP tour is at most the cost of the full doubled tree walk, which is 2 times MST. With this bound in place, we can now finish our approximation ratio analysis. Building on that doubling and shortcut trick, let's now prove why this algorithm gives a 2 approximation under the triangle inequality. First, we introduce 3 cost measures. H is the cost of our approximate tour, H10s is the cost of the optimal tour, and T is the cost of the minimum spanning tree. Since every tour must contain some spanning tree, we immediately get MENAC, T, is less than or equal to H10 Rafanitu, INAC. Next, our algorithm doubles every edge of the MST to form an Eulerian circuit and then shortcuts repeated vertices. This guarantees H is less than or equal to 2T. Combining these inequalities yields H is less than or equal to 2, T is less than or equal to 2, H times dot will, or equivalently H times H is less than or equal to 2. Short time. The row of diagrams at the bottom illustrates each step in action. Starting with points A through H, we build the MST, double its edges into an Eulerian tour, shortcut to produce our approximate tour H, and finally compare it to the true optimal tour H died. To see this in action, let's walk through the panels. Here we start with 8 points labeled A through H scattered in the plane. In the second panel, we pick an arbitrary spanning tree T that connects them. Then, if we double every edge of T as shown in the third panel, we get an Eulerian tour, but we also pay twice for each link. In the bottom left panel, we see the modified graph H, where some edges are duplicated but others are used only once. Finally, the bottom right panel shows H tied, the optimal tour, which cleverly avoids doubling particular edges while still visiting all nodes and returning to the start. This example shows we don't have to double every tree edge to achieve the best possible tour. Building on that, let's now turn to the minimum weight perfect matching problem. In a general graph G, a perfect matching is any subset of edges covering every vertex exactly once. When each edge carries a weight, our goal is to pair up all vertices so that each vertex is incident to exactly one chosen edge, and the total sum of those weights is as small as possible. Jack Edmonds gave us the first polynomial time solution back in 1965, running in O(n)² time. In the illustration, you can see the red edges forming a perfect matching. They touch each vertex exactly once while keeping the overall weight to a minimum. Before we start pairing up those odd-degree vertices, note that a minimum spanning tree can leave some vertices with an odd number of incident edges, yet these odd-degree vertices always come in pairs. This follows directly from the handshaking lemma, which tells us that the sum of all vertex degrees in any graph equals twice the number of edges. Because that total is even, there must be an even number of odd-degree vertices. Grasping this parity constraint is crucial. It sets the stage for matching up those odd-degree vertices in our next step. Building on that insight, once we've constructed our minimum spanning tree, some vertices inevitably end up with an odd degree. Thanks to the handshaking lemma, which tells us the sum of all vertex degrees equals twice the number of edges, we know the number of odd-degree vertices must be even. In other words, every MST guarantees an even count of odd vertices, setting us up perfectly for the next step, pairing those odd-degree vertices in a minimum weight perfect matching. Building on that, in any graph, the number of odd-degree vertices is always even. Let's call that set V. So how do we make every vertex even? We simply pair up the vertices in V-veris by adding only the edges of a minimum weight perfect matching. Once those edges are in place, each vertex has an even degree. Voila! The augmented graph is Eulerian, admitting a tour that traverses every edge exactly once. Euler tours are cycles that traverse every edge of a graph exactly once. A classic result tells us such a tour exists precisely when all vertices have even degree. So now that every vertex in our augmented graph has even degree, it's Eulerian and admits an Euler tour. On the left, you see a subdivided square with a single continuous red curve that covers each red segment exactly once, an elegant illustration of an Euler tour in a planar grid. On the right, there's a 9-vertex graph. The thick gray outline shows the overall cycle, while the yellow arrows mark the step-by-step traversal. We start at vertex 1, then move through 2, 4, 5, 8, 9, 6, 7. Back up to 5, down to 6 again, on to 3, and finally return to 1. Since every vertex here has an even number of incident edges, the graph admits this complete, non-repeating edge tour. Now that we've seen how Euler tours cover every edge exactly once, let's see how algorithm 2 puts that idea to work. First, we build a minimum spanning tree over all the vertices. Next, we identify which vertices in that tree have odd degree and compute a minimum weight perfect matching among those odd degree nodes. We then add the matching edges back into our tree, guaranteeing every vertex now has even degree. With this augmented graph in hand, we construct an Eulerian tour that traverses each edge exactly once. Finally, as we walk through that circuit, we shortcut past any vertex we've already visited, recording each vertex only the first time it appears. The result? A valid TSP tour. Building on that, here's a concrete example with 8 points labeled A through H. To the right, you see the minimum spanning tree over those points, with 2 subtrees highlighted, one rooted at B and the other at E. Below, we've doubled every edge of the tree and drawn an Euler tour that starts and ends at A, visiting each edge exactly once. That tour produces the sequence A, B, C, H, B, E, F, G, E, D, A. To convert this into a valid TSP tour, we shortcut any repeated visits by recording each vertex the first time it appears. The resulting approximate route is dot A, B, C, H, E, F, G, D, A, dot, which guarantees a 2-factor approximation to the optimal tour. Building on our previous approach, and thanks to the triangle inequality, anytime we shortcut an Euler tour, we can only shorten it. Here's how it works. First, we build a minimum spanning tree over all our points. Next, we add a minimum weight perfect matching on the tree's odd degree vertices. Together, those edges form an Eulerian graph, whose tour cost is simply the sum of the MST cost and the matching cost. Since the MST alone is already no more expensive than the optimal TSP tour, the cost of our Euler tour is bounded by OPT plus the matching cost. Finally, we shortcut repeated vertices to produce a valid TSP tour, whose length can't exceed that Euler tour. In the example at bottom left, the black edges show the MST and the red edges indicate the matching we added. The raw Euler tour visits every edge in this order: A, B, C, H, B, E, F, G, E, D, A. And by skipping repeated visits, we arrive at our approximate TSP route: A, B, C, H, E, F, G, D, A. Next, what's the cost of our perfect matching compared to the true optimum? To see this, we start with HTOS and optimal TSP tour on all vertices and isolate V, the set of odd degree vertices. By shortcutting H skipping over every other point, we obtain a subtour H that visits only V. Thanks to the triangle inequality, each shortcut can only shorten or preserve distance, so cost H is at most cost H trained. In the left diagram, you see the odd degree vertices highlighted. In the right, those detours are replaced by direct edges, illustrating that the subtour, and hence our matching, never costs more than the optimum tour. Building on our previous bound, we now turn our attention to H-daniness. We define H-daniness as the union of two perfect matchings on the reduced vertex set V-daniness. Since the two matchings together form H, at least one of them must cost no more than half of cost H. Immediately, this gives us a bound on the minimum perfect matching for V. Its cost can't exceed cost H/2. And because we already know cost H is strictly less than OPT, it follows that the cheapest perfect matching on V has cost under OPT/2. On the left, you see the original tree T with vertices labeled A through G and edges marked in red to form two matchings. On the right, those same matchings are combined into H-tour circled in red, and one of the matchings is highlighted in blue. That blue matching demonstrates there exists a perfect matching whose total weight is at most half the weight of H-tour and therefore below half of OPT. Building on that matching bound, we now invoke the triangle inequality to show our approximate tour can never cost more than the corresponding Eulerian tour. In fact, the Eulerian tour's total cost splits neatly into two parts: the cost of the minimum spanning tree plus the cost of a minimum perfect matching on the odd degree vertices. Since the MST alone is never more expensive than the optimal TSP tour, and the matching can add at most half of OPT, the combined cost stays below 1.5 times OPT. In other words, cost approximate TSP less than 3/2 OPT, giving us a 1.5 approximation algorithm, neatly improving on the earlier factor 2 approaches. Having just seen how our tour stays within a 1.5 approximation of the optimum, let's step back and look at three fundamental criteria for evaluating any algorithm. First, feasibility. The algorithm must always deliver a valid workable solution, no exceptions. Second, tractability. It should run in polynomial time, so we can scale to larger inputs without hitting an exponential time wall. Third, quality. Its performance must be provably close to optimal, which is usually our top concern when designing or choosing an algorithm. By satisfying all three, feasibility, tractability, and quality, we achieve both practical utility and strong theoretical guarantees.